Welcome back to CS 111. In this lecture, we're going to take a look at one of the most common types of data structures, the list. And we're also going to see how we can make a linked implementation of a list. So let's go ahead and dive into lists. At the start of the semester, we saw how we could go and use a basic type of data structure known as a bag that would allow us to go and store objects when we don't care about what their order is. A bag is an unordered type of data structure. We also saw several different types of data structures that had specific purposes in mind. Sets are for unordered data like a bag, but they don't allow us to store duplicates. We saw queues for when we want to be able to store and retrieve things in a first in, first out order. Stacks when we were looking for things in last in, first out. Priority queues if we want to go through and have some sort of priority that we could attach to items that would go and sort them when we went and retrieved the values that we had stored. And we saw decks or double-ended queues, which would allow us to go and add and remove things from either end of the deck. Priority queues behave a bit differently since there is some internal sorting going on when we go to retrieve values. But the other types of ordered data structures that we've looked at, queues, stacks, and decks, have predictable behavior in that the order that we go and get the items back from our data structure is dependent upon the order in which we went and added them to the data structure. So we do get control with these as in terms of how our values actually get stored. It just depends on the order that we go and load them into the data structure. The thing is, with these approaches, we're still only able to go and access elements at one end or the other, or in case of decks, both. We can't get to any values that are stored in the middle of the data structure, at least not without going and removing a bunch of things from the one end, so that our item goes and advances to the end of the data structure. That's a pretty significant limitation. If we want to be able to store values in an ordered fashion, and we want the ability to be able to go and access any element that we have stored without first having to potentially go and remove other items, arrays have traditionally been the solution for this. We saw them earlier in the semester here, and we've actually used them in implementing some of our other data structures. But arrays are nice because they go and store things in an ordered manner. We have an index that goes and uniquely identifies each item inside of our array, and there's a natural ordering to the numbers for the index. And by virtue of having that index, we can go directly to that location to go and store a value, retrieve a value, or modify a value that's already there. Now, while those are some nice upsides to arrays, there are some pretty significant limitations. The biggest one, as we've seen, is that arrays themselves cannot be resized once they're created. They're fixed sizes in memory. So if we have an array and we discover that we need the ability to store more items, we actually have to go and create a new larger array and copy the values from the first array into the second one. And that's not really efficient. It can require a lot of memory and a lot of work to go and transfer values if we have large arrays, and it's just kind of a pain to have to go and manage that. Arrays themselves are also not particularly user-friendly. They don't have any built-in methods or tools for being able to go and manipulate the values. If I want to go and store a new value in the array, I need to keep track of which elements I've used so far, for example, to figure out where I should go and put my new item. Or if I want to go and remove a value, then I need to have some strategy for keeping track of the fact that that item has been removed. That could be going and marking it with something like null, or going through and shifting the other values, and then just kind of keeping track of the start and end with those indexes for what we're actually going through and using. But none of these are really all that easy to go and use when we're actually trying to work with our data. Because of the difficulties with working with arrays, pretty early on in object-oriented programming languages, you started to see solutions for more flexible ways of being able to store ordered data. C++ originally went and created what's known as the vector. And Java has its own implementation of this in the java.util.vector class. The vector basically is a wrapper class that goes and stores an array internally, and it goes and gives you some additional functionality that makes it a little bit easier to work with the vector than if you had to go and interact with the array directly. It can go through and automatically resize by creating a new larger array if it needs to go through and make sure that it can store however much data you need. And it also goes and provides some methods for inserting and removing values. So this was a fairly early approach, but it's one that, at least in a Java context, has fallen out of favor. If you go through and look at Java's documentation, the vector class is considered to be deprecated. And basically what it means is that it is no longer recommended for use. And the reason why is that Java's vector implementation is pretty slow. It does not perform very well. If you're used to the C# programming language, just want to mention that there is a vector class there, but C#'s vector is actually something that is completely different than the vector that you see with Java or with C++. C#'s vector type is what's known as an immutable type, that once you go and store values, you can't change them. So it's got the same name, but different concept. Nowadays, lists are generally the preferred way to go and store ordered collections of items. They're very versatile, and for that reason, they're pretty much used just about all the time that you need to be able to store data, that you don't have a need for some of the specific functionality of one of the other types of data structures. So if I just need kind of a generic all-purpose place to go and put things in, I'm probably going to go and do a list nowadays. Storing data in an ordered manner is something that's really common in programs, especially as we start to design software that is very data-centric. So things like going and getting results from a database query, going and displaying information on screen in an application or on a web browser, working with things that are stored in files, going and managing tasks that we have to do. These are all things where it's pretty common to have some sort of ordering for it, and we would go and often use a list to keep track of what we need. Even in cases where we don't really have a particular need for ordering, it's still pretty common to go and use a list as opposed to a bag or something else, because lists have the ability to go and refer to individual items by an index number. And this is something that is a nice feature for us to go and have available to us. By going and using an index number, we're able to go and directly access individual items, like if we want to go and change what they're stored, or if we want to, for example, be able to go and iterate over and see what's all in our list without going and having to remove things first. So the ability to go through and access things by an index number is a really helpful feature to have available, and for that reason, even if we really don't care about order per se, we often will still gravitate towards using a list. So let's say here that we want to go and actually implement a list. What different operations do we want it to support? What methods do we want to go and include in our interface? Well, as we've seen with all of our other data structures, we've got to have a way to go and create a new list. And our constructor method will take care of this, and as we know, constructors don't get listed in interfaces. But everything else that we want to require for our list will be in part of the interface. One of the common operations that we're going to see is the ability to go and just add something to the list without having to specify specifically an index where we want to go and store it. In this case, what's going to happen normally with most list implementations at least is that it's going to go and store the item after everything that is already there. So it'll go and have the highest possible index, so whatever the current highest index is plus 1. We can generally also go and add items at a particular index. So I can go and say that I want to have something, say, at index 1. And what'll happen in that case, if I'm going and adding a new item, is it's going to take anything that was at index 1, since that's where I'm going and doing my add, or higher, and it's just going to go and bump it back one location. So the item that was index 1 before is now going to become index 2, and so on. Now, when we go and specify an index, there are some constraints on the index that we can go and use here with a list. The index can't be a negative number. 0 is going to be the very first element at the front of our list, so that's the lowest possible index we can specify. We also can't have any gaps in our index numbers. So if I have, for example, 5 items numbered 0 through 4 right now, I can't go and add a new item that would be index 10. The highest value I could specify for my new index is 1 more than the existing highest index. So the range of values I would have here, if I have 5 items right now, for an index to go and add something would be 0 through 5. When we want to go and remove items from our list, we're going to provide a single method, and this one's going to take a parameter with the index of the item that we want to remove. Now, this is kind of a little bit different behavior than how we added. When we went and added, we had a version that would allow us to add up at a particular index, or there was just a plain add that just said take this value and it would automatically figure out what index to go and use. It would go and stick it at the rear end of our list. I'm not going and providing that sort of method, one that doesn't take an index, for remove, because normally we want to be fairly deliberate about what we're going and removing. And if I want to remove from the front of the list, I can just specify index 0. If I want to remove from the rear of the list, I can just go and take the size of my list minus 1 to go and get that item. Now, if I really wanted to, I could go and code up some simple one-line methods that would just go through and basically go back and call remove and pass index 0 or this dot size minus 1 to go and get the front or rear and remove those. But those are less commonly used sorts of tasks. Normally we're being pretty particular about what we want to remove, and that's kind of in contrast to adding, because when we're adding, a lot of times we have a whole bunch of data that we want to add. We don't want to have to keep track of an index. We just want to stick it all in the list. So just calling the version of add that only has one parameter is really convenient there. That's not normally as much of a need when we go to remove. For all of our methods that take an index as a parameter, they're going to throw an index out of bounds exception if an invalid index is specified when calling the method. Any index that is less than 0 is going to be invalid for all of the methods. For the add method, the allowed range of indexes is going to be 0 through size, because size is going to be equal to the highest number existing index plus 1, because we don't want to allow gaps in our index numbers when we go and add new things. For methods like remove that interact with things that are already stored in the list, the valid index range is going to be 0 through size minus 1, because that's going to cover the range of index elements that we're actually using. Now, in the case where we go and try to, for example, remove index 0 and we have an empty list, we're still going to go ahead and throw an index out of bounds exception. Here with this implementation, I'm not breaking out that we have empty versus index 0 being invalid. If it's an invalid index, no matter why, I'm just going to go through and throw index out of bounds exception instead of having to mess around with no such element exception or illegal state exception for that one sort of edge case. The list really shines in its ability to allow us to retrieve and modify values that are already stored in the list at a particular index. So we're going to have a get method that'll take an index to go and return the item that's stored at that particular location. And we'll have a set method that will allow us to go and specify a new value to be stored at that existing location. Set presumes that the index that we specify is something that we want to overwrite the existing value of, whereas add will go and create a new item in the list at that position and bump back everything else. That's the difference between set and add. We'll also go and include some methods that will allow us to see what's stored in the list. We'll include an index of method that will go and allow us to locate an item inside the list. It's going to go and search and try to find the first instance starting at index 0 and going forward. If the item is not stored in the list, we'll have index of go and return -1. And that behavior with return value is something that we'll want to make sure that we include in the Java doc for this method. For convenience sake, we'll also go and include a contains method that'll return a Boolean value, just saying true or false if an item is stored. We're going to have a clear method that will go and remove all the items from the list and basically reinitialize the list. We'll throw in an isEmpty method that will go and tell us if there's stuff stored in the list, and a size method that will tell us specifically how many things are in the list. And then we're going to include two methods for going and exporting the contents of the list to an array. We'll have one that goes and returns just an array of objects, and then another one that will go and take a parameter with the type of array we want to use to store our results in. And this is a way to get around limitations in Java with generics. We've been doing mostly with just the object array implementation here as we've been working with other data structures. I'm going through and doing the second version here that takes the parameter just so that our list implementation is really going to be full featured here. That's something that's really nice to have when you're working with a list, so I've elected to go and add that additional method here. Now that we've figured out what we need to have, let's go into Eclipse and go and code up our new interface. Here in Eclipse, I've made a new project for our list interface, and I'm going to go ahead and make a package in here. Keeping with our naming conventions, I'm going to call this edu.wvu.cs111.listadt. And inside of that package, we'll go and make our new interface. I'll go ahead and call this list interface, and I'll click finish from the new Java interface wizard in Eclipse. So I've got my new interface here. We want to allow a generic parameter so that we can specify what type of data we want to store in the list. So I'm going to go ahead and add that generic parameter t. And I'll also provide some Java doc for my interface. So this is an interface for representing lists. I'm going to go ahead and specify my author name, and then I'm going to list that that parameter t is the type of data to store. And let's go ahead and work through the list of methods that we want to support with our interface. We have a whole bunch of them here. We'll start off with our add methods, and these are going to both return void. We'll have one that'll just take a single parameter of type t that we're going to call item with the value that we're going to store for when we're going and adding at the rear of the list. We'll have another version of add that will first take an int with the index that we want to add at, and then our item of type t. We'll have another void method to go and clear the contents of our list, and we'll have a Boolean method to go and see if the list goes and contains the item of type t. As you can see, I'm working through these in alphabetical order. We're going to have our get method that will return the item that's stored at a particular index, and since we're storing values of type t, that's going to be our return type here. This is just called get, and its parameter is going to be an int that I'll call index. We said that we wanted to have an index of method to find the location where a particular item is first stored in our list. So since we need to determine location, we're going to have to return an int for that. I'm going to call this index of, and then it'll take a parameter of type t with the item that we're trying to look for. I'll include a Boolean method to tell us if the list is empty. For going and removing things, we're going to have a remove method, and this will return the value that we removed. So it's going to return an item of type T. We'll call it remove, and then we're going to go and specify an int with the index that we want to remove. For being able to go and change things, we're going to have a set method, and we're going to have our set method return the existing value that is stored at the location. So we're going to actually return type T for this one. It's not going to be a void. Set is going to be the name of our method, and it'll take the index as an int that we're trying to modify, and then we'll go through and provide our new item to go and store at that location. We're going to have our size method that will return an int with how many items are on the list, and then we have our two different toArray methods. We'll have the one that goes and returns an array of objects, and this version of toArray does not take any parameters. And then we'll have another version that'll go and return an array of T-type items, and this version of toArray is going to go through and take a T-type array that we'll call destination array. And then I want to go and provide some JavaDoc for each of these methods. I went and finished filling out the JavaDoc for each of these methods. I made sure to go and note the exceptions that might be thrown with the methods that take our index parameter and that can throw the index out of bounds exception, and indicated what will go and throw those exceptions. And I also made sure that for my index of method that I went and listed how the return values here work, including that it's going to return a -1 if the value is not present. That way somebody who's going and using this method knows what to expect. Now that we've learned some of the basics of lists, let's take a look at how we can go about implementing a list. When working with lists, there's two major approaches to how we can go and implement them: using a linked chain of nodes or with an array. Both are fairly common, and each style has its own benefits. If we're going through and working with linked chains of nodes, it becomes pretty easy to go and add and remove elements. Arrays, on the other hand, allow us faster access to get to existing elements that are already stored. So in some extent here, it kind of depends on what you're actually expecting your most common operations are going to be with your list as to what style of implementation you might want to go and use. In some cases, it actually also depends on the language itself. With Java, array lists tend to be somewhat more common. They're kind of end up being the sort of the default. Whereas with C#, you'll tend to see linked lists used more commonly. But both options are available with native built-in implementations depending on your own preferences and needs. In this lecture, we're going to be focusing on linked list implementations. And within linked lists, there's actually a couple different types of approaches that we can use. To some extent, which one we choose might depend on our own personal preferences, but they also have some different performance characteristics that, depending on how we're expecting to use our list, might tend to favor one approach or another. The most basic type, and probably also just because it's also the simplest, the most common, is going through and using a linked list here that has singly linked nodes. So as we saw earlier this semester here, when we have singly linked nodes, each node is going to be its own separate object that'll have a field to keep track of a piece of data, and then it'll have another field that's going to go and point to the next node in the chain. And so we'll just keep on going down, following these next node fields to link to each successive node in our chain until we get to the last node. And for that one, the next node field will be set to null. At a minimum, we're going to have a field in our list object that will go and point to the front node in our chain, sometimes also called the head node. If we have that, we're able to go and access all of the nodes that are stored inside of our linked list. Sometimes you'll also see fields in the list object for other places, like being able to get directly to the rear of the list. depending on what sort of operations you're intending to do, sometimes that can have a performance benefit to go through and have like a field that also goes and points to the rear. It also can lead to a more complex implementation. So there's trade-offs with how we might go and choose to actually design our code. But overall, singly linked lists are pretty easy to implement, with the really big drawback being that we can only go and traverse them in one direction. So we have to be careful when we're going and coding because we really don't have a way to go backwards with those singly linked nodes. Doubly linked nodes are also used pretty commonly with linked lists. The advantage here is that we have the ability to traverse a list in either direction. We can go forwards or backwards. And depending on what we're intending to use our list for, that is something that can be useful to us. Doubly linked nodes are more complex to implement because we have more fields that we have to go through and potentially change as we go and add and remove items from our linked list. When we're going to implement a doubly linked list, you're normally going to see a front node and a rear node as fields stored inside of your list class. That way you can get directly to both the front and the back of your linked list. If you can't get directly to the back, you can make do without it, but it eliminates some of the advantage of being able to traverse that list in either direction that you get from having a doubly linked node. Another style of linked list that you'll sometimes encounter, although much less often than a singly linked or doubly linked list, is a circular linked list. You can implement circular linked lists using either singly linked or doubly linked nodes depending on your preference. The main difference from this type to the other types is that there's not a defined start and end or front and rear of our list. Instead of having the last node in our chain go through and point to null in its field that's pointing to the next node, or if we were dealing with a doubly linked list, the first one, its previous being set to null, what's going to happen is they actually go and loop back around. So you can see here with this diagram on screen, the last node in the chain actually goes and loops back around and points back to the first one. The major advantage to this approach here is that you can pick any node to start from, and you can just kind of loop back around. So sometimes this can be kind of helpful depending on what you're doing. Just kind of keeping track of, where my last position is. For example, maybe if I'm going through and inserting nodes here, maybe I want to go through and just kind of keep track of the last node that I inserted and make that actually be my front node pointer. And then I just go and advance one, and then I go and circle back around. Like I said, these ones tend to be much less common. Normally there's sort of niche applications where you might think about going through and using this. Most of the time, people just stick to regular singly linked or doubly linked list. For this lecture, we're going to focus on creating a singly linked version of our list implementation. We're going to store the data using nodes of the singly linked node class that we previously created this semester. I've provided this class as part of the starter code for this lecture. So you want to make sure that you download the starter code and go and import the nodes project into your Eclipse workspace. Now I'm doing a little bit of a variation here on the singly linked list in that my class is going to have a field to keep track of the front node and also a field for the rear node. The reason why I'm making the field for the rear node is that we said that we were going to have an add method that would go and add at the rear. So I'm expecting that that operation of going and adding at the rear will be used pretty frequently, and it's going to be faster for going and doing that if I can go directly to the rear rather than having to start at the beginning and iterate over things. It's going to be a constant time big O of one operation instead of a linear big O of n operation. So that's a trade-off that I think it's worthwhile for the performance gains to go and do the extra work to implement that field for keeping track of the rear node. Let's go ahead into Eclipse and see how we can code this up. Here in Eclipse, I've imported the starter code for this lecture. I went and made a new project called Singly Linked List, and inside of it, I went and adjusted the project properties under the Java build path to go and list my list interface and nodes projects as part of the class path, so that I can make use of the class and interfaces from those. Inside a Singly Linked List, let's go ahead and create a new package for our class. I'll call this edu.wvu.cs111.singlylinkedlist, and I'm going to go ahead and click Finish here. And then I'm going to go and create a new class inside of that package, and I'm going to call this class Singly Linked List. Down under the interfaces section, I'll tell it to add, and I'm going to search for list interface from my list.adt package. And I'll go ahead and click Finish. I need to go and add a generic parameter to my Singly Linked List class, so I'm going to use the tgeneric here, so that goes and matches up with the tgeneric used for list interface. I'm going to hover over the name of the class and use the quick fix here in Eclipse to go and add the unimplemented methods that we're going to have to code. And then I'll provide some Javadoc for my new class. So this is a singly linked implementation of a list. And I'll go ahead and provide my name and the tgeneric parameter as the type of data to store. Let's go ahead and create our fields for our new class. And as we said, we're going to have 3 fields. They're all going to be protected. Our first one will be a singly linked node to the front node of our list. We'll have another protected singly linked node that's going to be the rear node of our list. And then we'll have a protected int to keep track of the size. I'm going to use the quick fix to go and import the singly linked node class. And then I'll provide Javadoc for these fields. When we go and call a constructor to create a new instance of a singly linked list, we have a little bit of setup we need to do. We want to go and make sure that our fields that point to the front node and the rear node are both set to null to represent that we don't have anything stored in our list. And we also want to go and set the size field to 0, again, to show that we have an empty list. In our implementation here for the list, we said that we were going to have a clear method to go and basically reset the list, get rid of everything that's already stored there. That clear method is basically going to do the same things that we need when we go and run our constructor. We're going to go through and set our fields to null, and we're going to go and set the size to 0. So rather than going through and duplicating code between the constructor and my clear method, I'm just going to go through and code up my clear method here, and then we'll have our constructor written so that it goes and calls clear to actually go and do the setup work. I'm going to go to the clear method here, and inside I'm going to go and set the front node and the rear node to null to reflect that we have an empty list. So I'm going to say this dot front node is equal to null, and then I'll do this dot rear node is equal to null. And I said that I also want to go and set the size to 0 so that if it's 0, we know that there's nothing stored. So I'm going to say this dot size equals to 0. Let's go ahead and code up our constructor now, and that I'm going to do something I want to place right after my fields. My constructor is going to be public and it'll be called singly linked list, and it's not going to take any parameters. So I'll have an empty set of parentheses afterwards. What I'm going to do in here is I'm just going to go and call the clear method. So I'm just going to say this dot clear. Clear doesn't have any parameters, so I don't need to provide any arguments when I call it. And it's just a void method, so there's no return values or anything to capture or deal with. I just have a simple call to it. Let's go ahead and provide some Javadoc for our constructor. So this is a constructor for a new list of singly linked nodes. Before we work on implementing any of the other required methods for our list, I want to take a look at a helper method that's going to be pretty useful to us. As we work with our list, it's going to be nice if we have a convenient way to go and get a node by its index. In the required methods, we have a get method that allows us to specify an index and get the value from that node, but it doesn't return the node itself, and that's what I'm really interested in. So we're going to create a helper method that will allow us to go and specify a particular index, and it's going to return an instance of the singly linked node class that corresponds with that specific node. For our method, what we're going to have to do is take the index that is provided, and we first of all want to see if that happens to be the rear node that we're looking at. This is going to help us take advantage of that rear node field that we went and created. And we're going to check to see basically, does the index equal this dot size minus 1, because that's going to be the index of our last node. If it does go and equal the index of our last node, we're just going to go ahead and return this dot rear node. That way we can just get directly to the point. Assuming that we're looking for some other node, what we're going to have to do is go and create a current node variable to keep track of our place as we go and iterate through our chain of nodes. And we'll initially set it to start at the front node. We're going to want to look at the index because that's going to go and tell us how many times we have to advance our current node variable to the next node in the chain. So for example, if I'm looking for index 0, I'm going to advance 0 times, which means current node is going to just stop at where it started, the front node. Let's say that we want index 2. In that case, I'm going to go and advance to the next node once and then twice. When we go and stop advancing, when we get out of our loop for doing that, current node is going to be pointing at the node that we want to go and actually return. So we can just go ahead and return our current node at that point in time. I'm going to go ahead and code up my new method that I'm going to call getNodeAt. It's going to be a protected method, and it's going to return a singly linked node with that tgeneric parameter. And I said I want to call it getNodeAt. It's going to need to take a parameter that'll be an int for the index that I want to retrieve. The first thing that I want to do inside of the method is make sure that the index that was provided is actually a valid index that corresponds with a node that I have. So I'm going to do an if statement for this here. And if the index is less than 0, because all indexes are at 0 or greater, or if the index is greater than or equal to the size of my list, and keep in mind that since I have 0-based numbering here, the largest possible index is going to be size minus 1. If either of those conditions are true, then I have an invalid index. So I'm going to go and throw a new index out of bounds exception, and I'm just going to provide a message that says invalid index. Assuming that we have a valid index, we're going to take a look to see if that index corresponds with the rear of our list, because I have that special pointer with the rear node field that will allow me to get there directly. So I'm going to say if index is equal to this dot size minus 1, because that'll be the index value for the rear node, then I'm just going to go and return this dot rear node. So now I'm at the case where I need to go and iterate to go and find the node that I want. It's someplace between the front and everything up to before the rear node. So we're going to go and iterate to our desired node. Here I'm going to go and create a current node variable, and initially it's going to go and be pointed at the front node. I'm then going to go and use a for loop to keep track of my advancing over the different nodes in the list here. I know from the index exactly how many times I need to go and advance. So for loop works out well for this. So I'm going to say for, and I'm going to have int I equals 0, while I is less than index, I'm going to go ahead and increment I. And inside, we're going to go and advance to our next node. So I'm going to say current node equals current node dot get next node, since we have that getter method for going and retrieving values from our node. Once we get out of our for loop, we should be at the node that we want with that current node variable. So I'm just going to go ahead and return current node. And then I'll provide some JavaDoc for this method. Here I've got the JavaDoc. Notice that I did make sure that I document that we throw index out of bounds exception in the event that we have an invalid index. While we're working on things here in Eclipse, let's go ahead and knock out our isEmpty method. So this method is going to be really straightforward. We're just going to go through and take a look at the size field and see if its value is 0. I'm just going to return the result of the expression this.size equal to 0. And if that expression evaluates to true, then isEmpty will say true. Otherwise, it's going to tell us false. Next, I'd like to take a look at how we can go and add things to our list. The simplest case of going and adding is going to be when there's nothing in the list yet. So in this case, when we go to add something, whether it be adding at the rear or adding at a specified index, we're going to go ahead and create a new node. And once we've gone and made that new node, we're going to update both our front and rear node fields to point at that new node. And then we just want to go and increment size to reflect that we now have something stored in the list. The next simplest case for going and adding will be if we're going to add at the rear of a list that actually has stuff in it. Here we're going to go ahead and create our new node still. But what we're going to do then is leverage the fact that we made that field to point at the rear node. We're going to go to the existing rear node, and we're going to set its next node field to point at that new node that we just made. Once we've done that, we're going to go and update our rear node field so that it now points at our new node, and then we go ahead and increment size. Let's head into Eclipse and see how to code this up. For adding at the rear, that's going to be the version of add that just takes one parameter. Let's go ahead and code it up. So what I'm going to do to start off is I'm going to go ahead and create my new node. Now, I'm not placing any restrictions on the values that I'm storing in the list. I'm okay with null. So I'm not going to go and check to see if item is a valid value. I'm going to assume that if I don't throw a compiler error, that we're good to go. To create my new node, I'm going to say var new node equals, and I'm going to go and call the constructor for the singly linked node class. I need to specify my generic type is T, and I'm going to use the version of the constructor that just goes and takes one parameter with the value that we want to go and store. This will go and initialize the next node for my new node to be null. Once I've got that new node, the next thing that I want to do is figure out if there's anything actually in my list yet. And I'm going to use the isEmpty method for this. If the list is empty, that new node that I'm adding is going to be the front node. So I'm just going to say this.front node equals new node. If the list is not empty, then what I'm going to do is hook it on to the back of our chain after the existing rear node. So we're going to set our existing rear node to point at the new node. For that, I'm going to need to use the setter method on rear node. So I'm going to say this.rearNode.set next node, and I'm going to set it to new node. So we're going to have a way to get into the new node coming at the front now. Once we've got that in place, we're going to go ahead and update our rear node field to point at it so we can go and get directly to it coming from the back side of our list here. So we're going to make our new node be the rear node. And for that, I'm just going to say this.rearNode equals new node. And then I'm going to go and increment the number of the items in the list. So this dot size plus plus. We also have the version of the add method that takes two parameters, with the value that we're trying to store and the index where we want to go and place our new item. Let's see how this method is going to work. And for our example here, we're going to assume that we'll be adding our new node at index 2. I'm going to start off the same as we did when we were adding at the rear by going and creating my new node. Once I've done that, I'm going to have to figure out which node is the node before where the new node is going to go. So for that, I'm going to create a variable to keep track of my current node, and I'll initially point at the front, and then I'm going to advance down the chain index minus 1 times. So since my index is going to be 2 here, I'm going to go through and advance down the line 1 time. The idea is that current node, when we stop our loop here to advance, should be pointing at the node that's going to be before, immediately before, where that new node goes. So B is index 1. That one's going to be immediately before index 2 for our new node. Once we have our current node advanced so that it's pointing at the node that will be immediately before the new node that we're inserting, we're going to go and take that new node and we're going to set its next node to be what current node is pointing at its next node. So the next node after our current node is D. So we're going to set node C's next node to also be D. That way we can get from our new node to everything else that's going to come afterwards in the chain. And then we're going to go and finish hooking our new node into the chain by setting the current node's next node to be our new node. So now we'll be able to go directly from B to C and then C to D. And to finish wrapping things up, we just need to go and increment the size field. When we're trying to add new items by the index, one special case that we need to account for is if we're using index 0. What we're going to have to do here is change up our process a little bit because we'll need to update what front node is pointing at. Here, we're going to start off by creating our new node, the same as we've done in the other cases. Once we have new node, we're going to go and set its next node to the existing front node. And then we can go and update the front node field in our list object to go and point at our new node. And then to wrap things up, we just need to go and increment our size field. So if we're going and adding at index 0, you can see it's actually a little bit simpler process because we don't have that case where we need to go and iterate to find the node before we're going to be inserting the new one. Let's go ahead into Eclipse and see how we can implement our version of the add method for inserting at a particular index. The 2-parameter version of add is going to be quite a bit more complicated than the 1-parameter version because we need to handle these different cases of what we need to go and update depending on what the index is. We're going to start off by going through and making sure that a valid index has been provided. And here we'll do an if statement, and we're going to have 2 conditions that will logically OR together for when we want to go and throw an exception. If the index is less than 0, we're going to throw an exception. Or if the index is greater than size. Size itself is a valid index when we're going and adding things because the index then is going to be immediately after the existing rear. So we can go and do that, but we can't have any gaps in our index. So if the index was greater than size, we would have some gaps with unused items. That's not okay, but it can be up to 1 greater than the existing highest index. So assuming that we have an invalid index, we're going to go and throw a new index out of bounds exception, and I'm just going to use the message that we have an invalid index. Once we've gone and validated our index, we'll go ahead and create our new node. So I'm going to say var new node equals a new singly linked node with the tgeneric parameter, and I'm going to go and pass the item that I want to store inside of that new node. Since the process for adding at index 0 is different, I'm going to address that now. So I'm going to see here if the index is equal to 0. If it is, what we're going to do is point our new node's next node at the existing front. So I'm going to say new node.set next node, and I'm going to set that to this .front node. And this will work whether or not there are items in our list already. If we have an empty list, front node will be null, so new node's next node will just be null. Once we've gone and set that, we're going to go through and make our new node be the front. So I'm going to say this.front node equals new node. So this will handle if the index is 0. Our else clause will take care of any other index. What we're going to do here is we're going to go and get the node before the new node that we're trying to add. Because since I'm dealing with a singly linked list, I need to kind of get to that node because I need to be able to go and set its next node field to point at my new node as I'm working through stuff here. Now, what I'm going to do here is I'm going to make use of that get node at helper method that we created. So rather than going and looping over everything here, I'm just going to go and say var node before equals this dot get node at, and I'm going to say that I want to get node index -1. So this will get me the node that's going to go immediately before where I'll be placing my new node. Once I have the node before, so this is effectively where we ended up with current node in our animation, we're going to go and point our new node's next node at the node before's next node. So I'm going to say new node.set next node, and I'm going to set it to node before's .get next node. So I'm just using the getter and setter methods here. And then we're going to go and place our new node after the node before it. So we'll say node before.set next node, and we're going to set it to our new node. When working with this version of the add method, one possibility is that the index that was provided is 1 greater than the existing highest index. If that's the case, our new node is going to need to become the rear. So we're going to have an if statement to catch that circumstance. So we're going to say here if our new node is at the end of the chain, we're going to set the rear node to it. So I'm going to do an if statement here, and for my new node, I'm going to make use of the isLastNode Boolean method, and that basically just checks to see if the next node field is null. So if our new node is the last node in the chain, what we're going to do is just go and set rear node to point at it. So that wraps up updating all of our various links so that we can get around inside of our chain. To finish up this method, we just need to go and increment the number of items in the list by doing this.size++. Now that we've added stuff to our list, let's see how we can remove things. Remember that when we go to remove, we're going to specify the specific index that we're trying to remove. There's going to be a couple different scenarios of how things will play out depending on how many items are in our list and which specific item we're trying to remove. The simplest case will be if we only have one thing in our list and we're going to remove it. So if I only have one thing in the list, I'm going to start off by going and creating a temporary variable so I can store the value from the node that we're going to be removing. Once I've got that value safely stored, I'm going to go and update my front node and rear node fields so that they're both null to signify that there's nothing in the list. And I'll also go and decrement the size field to 0 since, again, there's not going to be anything in the list. Once we've done all of that bookkeeping work, we can go ahead and return the value from the node that we removed. Assuming that we have multiple things in our list, the way we're going to go about removing them is going to be different depending on if we're removing from the front, the rear, or someplace in the middle. We'll start off here by looking at where we're going to remove from the very front with index 0. I'm going to create my temporary variable to keep track of the value that we're removing. Once I have that value safely stored, I'm going to basically cut out that node from my chain. So I'm going to update front node to point at the node that came after the existing front that I'm removing. So instead of front node pointing at A, front node is now going to point at the second node, B. Once I've done that, I'm going to go and decrement my size field. And we'll go ahead and return the value from our removed node. For our next case, we're going to look at removing something from the middle of our list. In this example here, we'll go and remove the node with index 2, so the one that's storing the value C. We're going to have to create a current node variable to keep track of what node it is that we're currently looking at. We're going to go and start off current node at the front, and we're going to advance it the index of the node that we're removing -1 times. So since I want to remove node 2, I'm going to go and advance current node once. The idea being here that current node is going to be pointing at the node before the one we're removing, and that's because we've got a singly linked list and I can only go forwards. Once I've got current node at the pointing at the node that's before the one I'm removing, I'm going to create a temporary variable to keep track of the value from the node I actually am removing, so current node's next node. We'll go ahead and update current node's next node then to go and point at the node that comes after the node that we're removing. So now B is going to point to D, and it's going to bypass the node that we're trying to get rid of, C. We'll go ahead and decrement our size field, and then we'll finish things up by going and returning the value from our removed node. Our final scenario will be where we're trying to remove the node that is at the rear of our list. Unfortunately, we're not able to take advantage of the rear node pointer when we're trying to remove that node. So we're still going to have to start off by creating a current node variable and point it at the front node, and then we're going to have to advance it. And here, again, we're going to advance index -1 times. So I'm trying to get rid of the node with index 3, the one at the rear. So I'm going to advance 3 - 1, or 2 times. So when I'm done advancing here, current node should be pointing at the node immediately before the one I want to remove. In this case, it's pointing at C. At this point, we'll want to go and create a temporary variable to keep track of the value that we're removing from the current node's next node. So we've got D here. We're going to go ahead and cut that node off the end of our chain by going and setting the current node's next node to null. So it's going to look like C is the end of our chain. But we still have a little bit of cleanup to do because we have that rear node field that's going and pointing at the node that we're trying to get rid of. So what we'll want to do is update that. We're going to go through and make the rear node field point at our current node. Then we can finish up here by going and decrementing the size field and returning the value from our removed node. Our remove method is going to be pretty complicated, but we're going to start off with a similar type check that we've done in other methods to make sure that we have a valid index. So I'm going to say if the index is less than 0 or the index is greater than or equal to this.size, then we've got a problem, because those are not numbers that are going to correspond with an existing item in our list. So we'll go and throw a new index out of bounds exception with the message that we have an invalid index. Once we know that we have a valid index, we're going to have to go and start thinking about the node that we're trying to remove. The way I'm actually going to go and code my implementation here is I'm going to create a variable to keep track of the node that we're removing. This is going to be a little bit easier for when I'm going through and doing some of the manipulations with the different links. So this is going to be a variable to store the node being removed. And so I'm going to say singly linked node with the T generic, and I'm going to call this removed node. And right now I'm not going to actually assign it a particular value. I'm just going to leave it as uninitialized there. What I'll do first of all here, once I have that variable as a holding place, and the reason why I basically made it there is so that I don't have scope issues with the thing we're going to be doing next. So we're going to go and determine if we are removing the front node using an if statement. So I'm going to say if the index is equal to 0, then we're removing the front node. I'm going to go ahead and get the node that we're removing and store it in removed node. So I'm going to say removed node equals this dot front node. I can just go directly to it. Once I've got that, I can go ahead and update the front node, and I'm going to make it go and point at whatever comes after the node that I'm removing. So I'm going to say this dot front node equals remove node dot get next node. I also need to go and address the case where the front node that I'm removing was also the rear node. So we're going to go and update the rear node if this was the only item in the list. And for that, we're going to check to see if the rear node is equal to remove node. And if that's the case, then this item was both the front and the rear because it was the only thing in our list. If that's what we're facing with here, we're going to go through and set our rear node to null. So I'm going to say this dot rear node equals null. Now let's go and tackle the case where we're removing something after node 0. We're going to handle this in an else clause. So we're going to remove a later node in our chain. And here what I'm going to do is I'm going to get the node that's before the one that I'm trying to remove. So I'm going to use my get node at method for this. I'm going to create this var that I'm going to call node before, and I'm going to go and set it equal to this dot get node at of index -1. And then I'm going to go ahead and get the actual node that we're removing, and we're going to make that be stored in removed node. So I'm going to say removed node equals node before dot get next node, since it's the node that's right after the node that came before it. At this point, what I'm going to do is I'm going to go ahead and update the node before to point at the next node after our removed node. So I'm going to say node before dot set next node, and I'm going to set it to removed node dot get next node. If we were removing the last node in our chain, node before set next node will end up being equal to null. I need to address the case here as well that I'm removing the rear node, and I need to go and update the rear node pointer. So we're going to go through and update the rear node if we removed it. So I'm going to go and say if this dot rear node is equal to my removed node, then what I'm going to do is set the rear node to be the node before. So this dot rear node is equal to node before. So that'll go and finish updating our links there. Once we get out of this if-else block, we've gone through and removed all the links that we needed to. We just have to finish cleaning things up here. So we're going to go and decrement the number of items in our list by doing this.size minus minus, and then we're going to go ahead and return the data from our removed node. So I'm going to return removed node.getData. In this case here, going through and just grabbing the node and stashing it in this variable was a little bit easier for going through and updating some of these links than initially just creating a temporary variable to store the value. So that's why I coded things that way. Next, let's take a look at the methods for going and working with the items that are already in our list. We'll start off with get. So this one's going to take an index and it's going to return the value that's stored at that index. This method's going to be pretty straightforward because we wrote that get node at helper method that will give us the node at a particular index. So all we have to do is just get the value from that node. So what we're going to do here is we're going to attempt to get our desired node. And here I'm going to say var desired node equals this.getNodeAt for index. And if the index is invalid, the code that we wrote inside our getNodeAt method will go and throw an exception. So I don't need to deal with anything about that here. Once I've got the node, hopefully, I want to go ahead and return the value from the desired node. So I'm just going to return desired node.getData. Our set method is going to be kind of similar, except for it's going to change what's stored in the node in addition to returning the existing value. For this method, we're going to start off by using getNodeAt to try to actually get the node at our desired index. So I'll say var desired node here, and it's going to be the same thing as we did before, this.getNodeAt for index. Once I have the node that we're going to go through and change, I want to store the value that's currently there in a temporary variable. That way I can go and return it when we're done with this method. So I'm going to say var old item, this is going to be my temporary field, and I'm going to set equal to desired node.getData. Then I can go ahead and set my new value. So I'll say desired node.setData, and I'm going to set that to item. That's going to be the new value we want to store. Once we've stored that, we'll go ahead and return our old item. So we'll just return old item. Let's go ahead and do our size method since we haven't tackled that one yet, and this one's just a simple getter. It's going to return this.size. Finishing things out here, we're going to have a couple methods that are going to involve us iterating over the items that are stored in our list. For this process, pretty straightforward. We're going to go and create a current node variable to keep track of which node we're looking at, and initially it's going to point to our front node. And then we're just going to go and loop to advance current node down the chain until either we find what we're looking for, in the case of our index of method that we're going to be writing here, or we run out of nodes to go and iterate over. And in that case, current node will become set to null and we can stop looping at that point. Let's go and tackle our index of method next. So this one is going to return the index that this specified item first appears in, starting looking from the front, if it's present, and if not, it's going to return -1. So for this, we're going to have to go and iterate through our chain to go and look for the item. So we'll go and iterate through our list to see if the item is found. I'm going to create a variable here to keep track of what index we're at. I'm going to initialize it to 0. And then I want to keep track of what current node I'm looking at. So I'm going to say var current node equals this dot front node. And then I'm going to have my while loop so that we can continue to go and advance and search each of the items. So I'm going to say here while current node is not null, I'm going to go and take a look at each node. And what I'm going to do when I check each node here is I'm going to see if item is equal to the value that's in our current node. Now, I have to watch how I go and code this because I'm allowing null values to be stored. So item here could be null, and the value that's actually stored inside of our node could be null. So I can't just take item.equals or go through and do current node dot get data dot equals, because if those values are null, I'm going to have a problem. But I can go through and use one of Java's methods from the objects class to go and do the comparison in a way that'll be safe for if I have null values, so that I don't have to worry about getting a null pointer exception. What I'm going to do here is I'm going to say if java.util.objects, and I'm going to use the equals method for that. In Eclipse, if I just start typing objects.equals, it'll go through and automatically import that class. It's a pretty common one. I just spelled it out here so that everybody knows specifically what I'm really talking about. So I just go and provide two arguments for the things that I want to go and compare. So I'm going to compare current node.getData and then item. So if they are equal, if that returns true, then I'm going to go and return IDX, the index of the current node I'm looking at. Assuming that we didn't return, we're going to have to keep on searching. So we're going to advance to our next node. So I'm going to say current node equals current node dot get next node, and then I want to make sure that I go and increment my index counter. So we'll do IDX plus plus. If we get to the point where we fall out of this while loop and we still haven't found the item, if we had found it, we would have returned already. We're going to go and return that -1 to say that the item does not exist. So we'll return -1. Our contains method is going to rely on index of to do the bulk of its work. For contains, we just need to look at the value that gets returned by index of. So we're going to check to see if the item is contained in the list, and for that we're going to return the result of the expression this.index of for item if it is not -1. So if the index of that we get back is not -1, that means that we actually have a real live index for the item and it is contained in the list. If we get -1 back, that means the item is not in the list, so we'll return false here. Let's finish things up here with our two array methods. And I'm going to start off with the one that does not take any parameters. This one's going to go and create a new array and use that to return the data. So we'll begin by going and creating our new array. I'm going to call it destination array. And I'm using that name just so that I'm consistent here with my other two array method. That way, destination array is the name of the array that I'm going to be storing the values in. I'm going to make this array be a new array of objects, and it's going to be sized just to fit the number of items that are in our list. So our size will be this.size. Once we've got that array, we're going to go ahead and iterate over our linked chain to populate it. So I'll create this IDX variable to keep track of which element I'm currently looking at with the array. We'll go ahead and make current node to keep track of which node we're looking at right now, and we're going to start from our front node, and then we'll loop while current node is not null. What we'll do here is we're going to store the value of the current node in our destination array. So I'm going to say destination array sub IDX equals current node dot get data. And then I'm going to have to increment my counter, so I'll do IDX plus plus, and I'm going to go and move to the next node. So I'll say current node equals current node dot get next node. And eventually we'll get to where current node's next node is null, and when that happens and current node becomes null, we'll fall out of our loop. And once we fall out of the loop, all we have to do is just go and return destination array. Our other version of toArray takes that destination array parameter. And this is a workaround for us not being able to go and create new generically typed arrays. I can go and create a copy of an existing one though, and that's why we're going and giving that parameter, so I can make a copy of it. What we're going to start off with inside of this method is figuring out if the provided destination array is big enough or if we need to make a larger one. So I'm going to check to see here if the destination array's length is less than the size of my list. If that's the case, I'm going to have to create a bigger array. So I'll go ahead and create my new larger array using the arrays.copyOf method. So I'm going to say destination array equals the new array that I get. I can just start typing in arrays.copyOf and Java will automatically go and import from java.util, but I'm just going to go and fully qualify the name here. So I'm doing java.util.arrays.copyOf. With copyOf, I need to go and provide the first argument as the array I'm trying to copy. So that's going to be destination array. The second argument is going to be the size I want for my new array. So that'll be this.size. So if the array is smaller, we're going to go and create a new array that'll be just big enough to store each of the items in our list. Otherwise, what we're going to do is we're going to go and fill the existing array with nulls. And that way, if I see a null value, it's not going to be quite perfect because I could have had a null stored, but it's at least going to go through and give me an idea that this is probably not an element that I was using, especially if I see a bunch of nulls in a row. I'm going to go here and say java.util.arrays.fill, and this is a void method, so I don't need to capture its return value. Here I need to go and specify as the first argument the array that I'm trying to fill, so destination array. And then the second argument is going to be the value that I want to store. So I'm just going to go and store null and everything. Once I've gone and got my destination array set, I can go ahead and iterate over it to go and fill the values. So this is basically going to be what we had in our other version of toArray. We're going to go and iterate over our link chain to populate the array. So I'll say int idx equals 0, and then we'll do var current node equals this dot front node, and we're going to loop while current node is not null. And inside here, we're going to go and store the value of the current node in our destination array. So I'm going to say destination array sub idx equals current node dot get data, and then we'll go and increment our counter idx plus plus, and we'll go through and then move to our next node. So we'll do current node equals current node dot get next node, and then once we get out of this while loop, we'll go ahead and return our destination array. So really kind of the difference between this and the other version of toArray is right out here at the beginning where we're going through and getting the array set up so we have someplace to store our data. With that, we now have a functioning implementation of a linked list. For this lecture's participation project, I want you to go and download the starter code for the participation project from eCampus. That starter code will go and contain the singly linked list class that we've gone and created here as part of this lecture, as well as our singly linked node class and our list interface. I want you to go and create a new class with a main method in it, and I want you to go and make an instance of a singly linked list, and when you're going and working with it, I want you to go and treat it like it were a regular queue. So you should go and add and remove items in first in, first out order. So you'll want to think about how you want to go and call the add and remove methods to go and get that sort of behavior. You'll need to store at least 5 values of your choice in the list, and I want you to go and remove and print those values in the order that they were added. When you go and turn in this project, you should only submit the class that has your new main method in it. That's where we're going to end things for this initial look at lists. If you have any questions, please join the Q&A session or send me an email. Thanks, and have a great day.